Okay. Okay, so today is October 14th, Wednesday, and this is ECE641 model-based imaging. And today we're going to pick up on the constrained optimization material. And as I was just saying, the key, what I'm really mostly going to cover, at least for this lecture and the last, is the introduction to that chapter. You need to read the details. I probably won't go into a whole lot of the details. They're important, but you have to read them, okay? Because I want to give you the big idea. The big idea. And one of the things I feel strongly about after many years of being involved in the research biz and the engineering biz is that in order to be effective in research and engineering, one must use both sides of your brain, okay? The right and the left side. Now, I think that may vary from individual to individual, but mostly the left side is like, who knows this? Neil, you should know. You're laughing, okay? Well, that laugh indicates that you don't know, which is good, because that means no matter what I say, you won't disagree. So the left is like abstract thinking or something like that, and the right is... Oh, it's the other way around? Right is abstract?
Thinking is left, and then I think right is like creative.
Oh, right is creative. So that's sort of abstract, creative. The left is more analytical or something like that. You need to use both sides of your brain and get them to interact in synchronicity, okay? Because some people, by nature, are like, well, what I might call more analytical, okay? And they're good at, often those people are more algebraic, okay? So they're like, oh, yeah, when they get up a head of steam doing their calculations, they're like in their zone, okay? And they're like, they're happy with that. And they're like, and that's how they think about the world, okay? But the problem is, no matter how good you are at that stuff, that, if you don't have a sense of where you're going, you'll end up just careening off into the weeds, okay? Like, 17 pages later, you'll have somewhere, I don't care how good you are, you'll have made a mistake, you'll somehow have gone down some very strange road, and you'll be just getting nonsense, okay? On the other hand, you have the people who are more the right brain thinkers that are sort of more the creative ones, okay? And those kinds of people are like, well, it's sort of like, the equation is sort of like the philosophy of the, whatever, the alien people from Mars who thought that the world was a never-ending loop, and it all sounds good, okay? But the problem is you really can't get any rubber to the road, okay? It's a lot of sort of deep philosophy, but it doesn't really go anywhere, okay? And, I guess, I don't know if it's really true, but supposedly Albert Einstein was supposed to have said something like, philosophers think about more and more, think less and less about more and more until they know nothing about everything, and physicists know more and more about less and less until they know everything about nothing. Okay? So maybe that kind of captures the philosophy, but you got to put both together. You have to be able to do the mechanics. You have to be, you might say, oh, I'm not good at, well, you know what, I don't care. You're not good at the mechanics, you need to practice the mechanics more, okay? Because you have to get better at that. Whether you like it or not, it may not be your thing, you may not think it's fun, so what? You just got to learn to do it better, okay? But it's not enough to just do that. You also have to develop the other side of your brain, where you think about the bigger picture and where you're going. Does it make sense? Do the equations mean anything, okay? Because without that, you have sort of no guiding principle. You're just a machine. You're just a drill bit, okay? Where are you going? It's like one of these machines that will drill a hole to the center of the earth, okay? But sooner or later, it's gonna, it's not gonna make it all the way through, okay? So you need both. You need you need the big sort of intuitive picture to guide where you're going, but you also need to be good at the mechanics. You have to develop, and most people are good at one, better at one than the other, and you probably know which one you feel more comfortable with. So you have to lean into it. You have to lean against the thing, rather than, okay, great, it's wonderful, you're good at something, so you try to develop that, but you also have to try to improve the thing that you're weaker at, okay? So both kind of try to balance those two sides. And with that thought, and given that what I'm talking about has nothing to do with image processing, I'll put this thing up here, which I think is kind of just cool. One of my students said that he had read this in its original form, and that it didn't really quite translate this way. But this is what the translation is that's popular. Sun Tzu was a great ancient philosopher who who wrote a famous book called The Art of War, okay? And this is one of his famous quotes: "Strategy without tactics is the slowest route to victory. Tactics without strategy is the noise before defeat," right? So in other words, if you're just but you have no idea where you're going, you have no overriding principle or viewpoint, then it's exciting, but it's not really producing anything. It's sort of like one of those jet skis where it's like spewing water up in the air and there's a lot of noise and heat, but it's not necessarily moving you faster, okay? And then, but a strategy without tactics, well, that's got issues also, because, when you kind of know where you're going, that's good, but you're not very good at getting there. So, yeah, interesting. So, okay, enough of that, I guess, but I kind of like it. So with that thought, I'm going to really emphasize the big ideas here, and I'll let you focus more on the tactics. I'm going to emphasize the strategy, because that's the part I can really do more effectively in a classroom environment. All right, and so we're kind of running out of chalk. So last time we talked about the fact that we want to solve a problem, x hat equals arg min over x of f of x plus h of x, right? That's our goal. But we're going to do this crazy thing where we're going to actually make the problem harder so that we can make it easier. So we're going to split the problem in two. I'm going to take a couple steps, I think, a few steps together here in the interest of saving time, being time efficient. So we have x and v, okay? But we really want to enforce the constraint that x and v are equal. So what we're going to do is we're going to have f of x plus h of x plus 1, so a over 2 of the norm of, this is v, x minus v plus u norm squared, like this. And then with u such that x equals v. In other words, we pick u such that at the minimum x equals v. And we can do that. I'll just put here x here, because even though we're minimizing over two things, they're going to be equal. We can do that because as we make u as u increases, right? As u increases, what will happen is that x minus v will decrease because they compete. They compete, right? They're kind of using up the same space. So as I drive this value of u up, then it's as if, because this energy function here looks like this, right? So if u is here, what'll happen is x and v look like that's downhill. Does that make sense? Because I'm adding x minus v to u, right? But if u is here, then x minus v, this looks downhill, right? So if u is negative, it will tend to drive x minus v up. If u is positive, it will tend to drive x minus v down. So if u goes down, then what will happen is that x minus v will go up. So they tend to move in opposite directions. You increase u, x minus v goes down. You decrease u, x minus v goes up. Okay? So there's got to be some value. Now, I'm sort of talking about in the scalar case, these really are vectors. So what will end up happening is that individual components of u can control individual differences between components of x and v. But let's just talk about scalars, because intuitively that's close. What will happen is I need to adjust u until the resulting value of x and v is 0. And that should work, assuming that assuming that h and v are say, convex. Let's assume they're convex, but certainly as long as they're continuously differentiable, then as I increase u, I should get a continuous change in the value of x and v, right? Actually, that's one of the theorems we have in the book, it's a continuous, the output is a continuous function when these are convex. So everybody gets that? Does that make sense? Yep.
How necessary is A now, since we have U?
Well, very good question. Well, let's see. If A is 0, then it doesn't work. If A is some finite positive value, so this will work for any positive value of A. So I can choose A however I want. So the interesting thing is going to turn out that the solution doesn't depend upon the choice of A. But what's going to happen is that the choice of A will affect the rate of convergence when we actually implement the algorithm. And the reason intuitively is, let me hold on that thought just a moment, write the algorithm down, and then I'll talk about why the choice of A is important. Essentially what happens is that there's two things. Okay, if A becomes larger and larger and larger, then the convergence of U will actually be faster because if A is large enough, you don't even need U. Okay, so with only a few iterations, so from that point of view of convergence in terms of the iterations, then it appears that there's no disadvantage to making A larger. But there is a disadvantage to making A larger. The disadvantage is that as A becomes larger, the problem becomes stiffer. And a stiffer problem is harder to solve. So there's two things that usually come up. One is that, let me write the algorithm out. So the algorithm is going to be repeat. It's going to be, what you're going to do is you're going to say x hat equals the arg min over, I'll make this x hat v hat. Oh, no, I'll do it like this. Hold on. So I'll go x v goes to arg min of f of x plus h of v plus a over 2 norm of x minus v plus u norm squared, right? And then u goes to u plus x minus v. And the idea is that I just argued here that as I increase u, x minus v goes down, right? So with each loop, I take whatever if x minus v is large, then I increase u so that x minus v goes down. That makes sense, right? You know, at least the control law is in the right direction. Okay? So that's good. So now what happened? And then also there's an issue of you have to initialize u. So we'll initialize it to 0. You don't have to initialize it to 0, but usually you initialize u to 0 in practice because it's not usually the case that there's any other initialization for u that makes more sense. So now what happens is when you solve this argmin, it might be that you have a closed form solution to this argmin. Okay? If you did, you probably wouldn't be using this algorithm at all, okay? Because if you had a closed form solution, then you just take the limit of that closed form solution as a goes to infinity, and you'd be done. So most of the time, you don't have a closed form solution to this, okay? So if you don't have a closed form solution, then usually what happens is you solve this iteratively. So this is really like a nested iterative loop. There are definitely issues associated with that because if one step in your algorithm takes an infinite amount of time, then it's not a very useful algorithm, right? And an iterative loop takes an infinite amount of time, but of course we make some sort of compromises. It's not perfect, okay? And we can talk about that later. But the point is this. So the problem is everybody knows the story of Goldilocks and the 3 bears, right? If you've taken a class with me, you probably know it before. Okay, so let me just go review that quickly for the exam, which is that Goldilocks was taking a walk in the woods, okay? And she kind of got lost, and she was hungry and tired. So she showed up at the 3 bears' house. And the 3 bears had decided to go take a walk themselves. So there was the mama bear, the papa bear, and the baby bear, okay? And so she went in and she sat in the papa bear's chair and it was too hard, and she sat in the mama bear's chair and it was too soft, and she sat in the baby bear's chair and it was just right, okay? And then she went upstairs and she said, then she got the porridge and the papa bear's porridge was too hot and the mama bear's porridge was too cold and the baby bear's porridge was just right. And then she went to the bed because she was tired, the bedroom, and she said Papa Bear's bed was too hard and the Mama Bear's bed was too soft and the baby bear's bed was just right, okay? And she fell asleep, and then the bears came home from their walk and they saw her, and I think, depending upon the way the version of the story you get, it either ends badly or well. We'll give you the nice ending where she ran away and went home and they all lived happily ever after. So the point of this story was, of course, to kill a little bit of classroom time, but also this concept of Goldilocks. Goldilocks, or Goldilocks? Is that how you spell Goldilocks? Okay, we're going to go with this, okay? Maybe it's one name, so it's an L like that, okay? Goldilocks. You'll read about it. You think I'm kidding. You think, boy, this guy's really lost it. But you'll read about Goldilocks in the newspaper all the time, okay? Why? Because they always talk about the Goldilocks economy, the Goldilocks this, the Goldilocks that. Have you read it before? Yeah, you've read it before.
About the right amount of inflation and unemployment.
Yeah, exactly. Did you know about this story about Goldilocks before this?
Yes, I think God knows.
Okay, because a lot of students have never heard the Goldilocks story, right? And they're like, what's this Goldilocks thing, okay?
It's definitely taught in India.
Oh, it's taught in India. Okay, there you go. But it's not always taught in all countries, right? Maybe it's taught in more places now because they always talk about the Goldilocks economy, okay? So the current practice, what is the Goldilocks value of A, okay? So the question is, so the problem is, if it's too big, one thing happens. If it's too small, something else happens. So then you just want it to be just right, okay? So too big. Too big. If it's too big, oh, well, we'll do too small first. Small. If it's too small, what's going to happen, and we can put some more meat on these bones later on, what's going to happen is that the convergence of this loop is going to be slow. Because what'll end up happening is that if there's a lot of slop in A, so slight A small, then what'll happen is that the first iteration, X and V, will be really far apart. And then you have to make a big change in U, okay? And then it's going to go completely someplace else, okay? So it's going to be big oscillations, okay? And they're going to take a long time to die down, okay? So if it's too small, you'll have slow convergence. So then you'd say, well, hey, I'll just make it really big. But if it's too big, there's another hidden problem. This algorithm here is going to be too stiff. So what'll end up happening is that solving it becomes hard. So effectively, what's going to happen, this kind of hides that problem, but effectively you got to solve this minimization, and solving that minimization becomes hard. So it becomes a trade-off, so too stiff. So it becomes a trade-off. If it's too stiff, that means the conditioning number is going to be poor. So it's going to be a very large conditioning number. So what ends up happening is there's a trade-off between you have the total computation is the computation per iteration times the number of iterations. So if it's too small, you'll have too many iterations. If it's too big, the computation per iteration is going to be too high. Okay, so that's the trade-off. Okay. Now, and it's actually very much of an active research area to try to figure out how to pick A. Okay, people usually just do it in some mostly do it in some ad hoc way. Now, but we're not finished. This is augmented Lagrangian. And this term here is called the augmented Lagrangian term. Because if it was just a Lagrangian, the reason it's called augmented Lagrangian is you have A over 2 times, what will end up happening is you have, so you have A over 2 times the norm of x minus v plus u squared, but that's equal to this times x minus v squared plus or minus a times x minus v transpose u plus a over a over 2 of norm of u squared. That's just if you expand it out algebraically. So this term, you're not minimizing with respect to u, so it doesn't really matter. You can just get rid of it, okay? It's not that it's 0, it's just that it doesn't have any effect on the minimum. This term over here, this is the augmentation term. That's why it's called the augmented Lagrangian. And this term here, this is the Lagrange. Oh, yes. Let me rewrite that. I'll put this over A because it's a scalar. This is the Lagrange term. okay? Because whenever you have a Lagrangian, you take something lambda transpose x minus v, because your goal is to set x minus v equal to 0. So you multiply, the term you add is this, and you pick lambda so as to derive that term to 0. So this is an interpretation of being solving the Lagrange problem. This is the Lagrange multiplier for a cost function which is augmented with this additional term. So that's where the expression augmented Lagrangian comes from. I can erase this, right? Because you know this part here, right? So now we have to go one step further into the woods. Hopefully we won't stop by the Three Bears house, I guess. So then we have a thing called ADMM. ADMM is called alternating direction method of multipliers. ADMM, okay? And you know, one thing that's kind of catchy these days is there's so many cute acronyms like backpack, or they'll take some kind of thing and that's they reverse engineer. And where I really knew they started getting cheesy was when they would use like pairs of letters and stuff to somehow get it to come out right, But you really know you're a first-rate researcher when you can give an algorithm something like a name like ADMM and it still sticks, okay? Because there's nothing catchy about it at all, okay? So it's sort of like one of those campy movies that's so terrible that people love it, okay? Okay. So anyway, ADMM, okay? Where did the name come from? Method of multipliers refers to any method. Basically, method of multipliers is an alternative terminology for Lagrange methods, okay? Because it's called method of multipliers because you multiply these things together, okay? So alternating directions is the unique thing here, okay? It's an alternating directions method of multipliers. And what you do is this, you say repeat. Okay, here's what you do. Instead of doing this minimization in one step, where you minimize over both x and v at the same time, you break it into two steps. So now, I'll write this over here. Okay, this is like an aside, okay, and then I'll erase it. I just want to go over this one thought. Okay, you remember coordinate descent optimization, right? Coordinate descent optimization is sort of a special case of a more general concept, which is that if you have a function which is a function of, say, x and v, and you want to minimize it, what you do is you do this. You say repeat. You say, okay, I'm going to take x, and I'll replace it with the minimum over x of f of x v. And then I'll take v, and I'll send it to the minimum. Okay, actually, this is the argmin. Argmin over v of f of xv, okay? And you repeat. That's called alternating minimization. It's just like I said with coordinate descent, where you have some kind of gizmo and you have two knobs on it. The one knob is x and the other knob is v, and then the output of this goes to a meter, sort of the happiness meter, okay? And you want to you want to adjust these knobs to maximize the happiness, right? So you turn this knob until you get the maximum happiness, but then you go here and you adjust that knob. And you keep going back and forth, because what ends up happening after you've adjusted both knobs, this adjustment is no longer the best. So you have to go back. So you keep alternating. If the function is continuously differentiable and convex, then yeah, then this this alternating direction method is guaranteed to converge to the global minimum. Yeah.
Is this just a special name for coordinate descent, or?
It's a little bit more general, but, well, I would actually say it's the same thing as coordinate descent. I kind of agree with you. But I think that maybe broadly in the community it's seen as a little more general, because coordinate descent's viewed as the special case usually when the pixels are scalar, but they don't really have to be scalar. V and X can be sort of general vectors, high dimensional vectors. So usually alternating minimization is associated with the case when you have high dimensional, these are high dimensional vectors. So like alternating minimization, like let's say you were doing deep learning and you had two pieces to the neural network. You could do training on the one piece and then training on the other and then keep going back and forth. But yes, it's basically the same thing as coordinate descent. Okay, in the theory literature, you'll see more theorems about alternating minimization, I think, than you'll see about coordinate descent. Although coordinate descent's become popular just in the recent few years, honestly. But it's been around for a long time, okay? So, so instead of doing this minimization, what you could do is you could say, well, okay, I'll do alternating minimization. So I'll do an arg min over x, okay, of f of x plus h of v. Don't write this down because I'm going to change it. I'm going to change it. Well, maybe you can write it down, but then you can delete the part that I'm going to change. Min over v of f of x plus h of v plus a over 2 x minus v, right? Okay? And then this update for the u is u plus x minus v, right? This is alternating direction of method of minimizing. Now in this case you have to initialize u to 0, and you have to also set v to some v init, okay? Because you'll need an initial value of v in order to minimize over x. And of course you could have swapped this order. It's the same thing. Well, it's not the same thing in the sense that you'll get a different result, but it's the same method. They're both considered ADMM. Okay. Now, the interesting thing is, for the special case of variable splitting, the function f is not a joint function of x and v. It's the sum of two independent functions, of two separate functions. So if you're minimizing with respect to x, this term doesn't matter, right? And if I'm minimizing with respect to v, this term doesn't matter. Okay, so now this has kind of an interesting interpretation. This minimization over x, I can actually rewrite this. Okay, this is like you're minimizing f, but you have this additional quadratic term over here. Let me not rewrite this. I'll erase this and rewrite the whole thing because I think it's important to be able to compare them visually. By the way, this is really cool. And this is a super useful algorithm. And there's a fair number of people who know about this, but it's not really super common knowledge, okay? It's not. So what you can do is this. You can rewrite it as repeat. What I do is I'll have x goes to arg min over x of, I have f of x plus a over 2 norm of x minus v minus u. Wow, I didn't make a lot of changes there, but it's kind of an important conceptual change. Then v goes to arg min over v of, this is going to be h of x plus a over 2 norm of, this is x minus, oh no, this is going to be v, okay, minus x plus u, I think. But let me double check that. Is that right? No, it should, yeah, that's, no.
That looks right.
Is this right? Hold on, let me see if I got the signs right here. So x is x, v is minus v, okay, and this is plus u, okay. Then that's v, this is minus x, and then this is minus u, right. I think this is correct. Interestingly, I wrote this down without actually looking at the signs because I'm terrible at algebra. I wrote it based upon my intuition about what it had to look like. Okay. All right. And then this is u goes to u plus x minus v. Okay. All right. Now, why did I go through all that trouble just to put a few terms, like move them around like that? Yeah?
It should be h of v, not h of x.
F h of v, yes. Beautiful. Why did I go through so much trouble? Because there's a very subtle thing going on here. And it's so subtle, it's a beautiful thing because you can write it down really easily, and then it all looks so nice. But sometimes the thing with beautiful things is you have to be careful because they're so easy that you miss them. You know, it's like magic. And you're like, how did he do that, right? So we have to go slowly, even though it's simple, I think. We can define a function, f of x. Oh no, we'll say f of v, say. Oh no, we'll say f of, maybe I'll use a new letter, just to f of z, so as not to confuse you. Of course, these are all dummy variables, so it doesn't really matter, but still, I know it's hard. So you have arg min over x of f of x plus a over 2 norm of x minus z squared. And I'm defining this. And then h of z is equal to arg min over v of h of v plus a over 2 norm of v minus z squared. Okay? The reason I did that is because this whole thing here then can be replaced with this first thing, x goes to f of v minus u. And this thing here goes to, v goes to h of x plus u, right? And then u goes to u plus x minus v. This is ADMM, right? But this is I think this is a much more compact way of representing it. Does everybody see why this is true? Because if I define these functions, then if I just put in for z v minus u, which I put in the parentheses, then that's true over there, right? So what's going on with this? So what's going on? Okay, first of all, turns out this is called a proximal map. If you know about proximal maps, people in the, like mathy people will think you're cool, okay? And it's not really that hard. So, you know, the coolness to effort factor is relatively high. Okay, so it's a lot better than having to learn, you know, some exotic abstract algebra thing. So, you know, like proving Fermat's last theorem or something, you know. So here's the intuition. What is a proximal map? So this is, let's consider the case of the function f of x. This is x, right? And then you have some value here, z, okay? So you start off at this, you're anchored to this point z, is the way to think about it. So the z is the anchor point. And now what happens is that you solve this optimization. Now, if a was 0, you just solve the optimization. So you give the value that minimizes f. But you don't do that. Instead, what you do is you solve the optimization subject to the fact that you have this additional term. Now, what is that additional term? Now, we've looked at this enough that we know that this is like the energy of a spring. Of course, this is a vector rather than a scalar, so it's kind of a vector spring, okay? But that's fine. Well, the intuition in 1D is fine. It generalizes. So now the spring is anchored to the point z, right? So what's going to happen is that rather than doing a minimization of f that's completely free, you have this additional term which has got a tether to an anchor point that's springy. So one interpretation I like to give, which maybe is, it's important to interpret my explanation is somewhat vivid, okay? But I assure you, during the entire discussion, the dog will be happy, okay? So we have like a person who's walking their dog, okay? Right? And I like dogs, okay? So nothing unhappy would happen to this dog. But let's just imagine that the dog is tethered by a leash which is springy, okay? Like this, okay? So the dog wants to go downhill, but the person has the leash. And the dog goes down to a certain point, and then the dog stops because it can only go so far, right? So then what happens, and this is the part where the dog, I assure you, is happy. You glue the dog to the function. But it's a happy glue, okay? So then what happens is that you glue the dog down, and then the person walks over the hair, and then the dog then you unglue the dog, and the dog goes down further. Okay? So the point is this, and this is, so we'll call it z prime. So what happens is that you have z, right? And then you say, okay, z prime goes to f of z. And then z double prime goes to f of z prime. And that's like the next point. So each application of this proximal map allows the dog to get closer to the global minimum, where the dog would be maximally happy. So the idea is this. A proximal map is just a fancy way of saying I'm going to minimize a function, but I'm not going to completely minimize it. I'm just going to partially minimize it. And the beauty of a proximal map is that you can keep reapplying it. And with each new application of the proximal map, you get closer to the minimum. So this kind of makes you, and at least for me, you go, well, okay, obviously, what I might want to do is this. I might start with a z in some initial value, and then I take z and I replace it with f of z. And I just keep doing that. And if I do that forever, eventually what's going to happen? I'll get all the way to the global minimum, right? So what will happen is in the limit as whatever, something goes to infinity, in the limit of Zn, as n goes to infinity, we'll say, is going to be Z star is going to be the solution to the problem. So that's the intuition behind proximal maps. And the word proximal means because what you're doing is you're finding a minimum, but a proximal minimum. So you're restricting yourself to stay within a neighborhood, and then you're finding the smallest value within a neighborhood. In the limit as a goes to infinity, so as the spring becomes very tight, this is going to be exactly like taking a step in the direction of the gradient. But for larger values or smaller values of a, it might differ quite substantially, okay? Especially if the function's not quadratic. So, okay, so you got this idea behind a proximal map. So in this context, the ADMM algorithm has the following interpretation. You're applying, you have like, f is a proximal map which maps you to a value which is, reduces f. H is a proximal map which maps you to a value which reduces h. So I use an uppercase letter for the proximal map and the lowercase letter for the function that the proximal map is minimizing. So each of these steps kind of moves you in the direction closer to the minimum of that function. And the repeated application of them, now if you just repeated them, if you just applied f and then applied h and applied f, you wouldn't converge because it would be like two people tussling over the solution to a problem. They would say, well, where are we going to go to eat? And I'm like, I want to go to Pizza Hut, and then I want to go to Burger King, and I want to go to Pizza Hut. You don't converge. Of course, there's a little bit of a problem. That's a bad analogy because the solution space there isn't continuous unless you could have a probability distribution over the space of places you could go to eat, okay? Maybe if you ask for what kind of beer, you could mix, you could do like they do at Nine Irish Brothers where they mix like Blue Moon and Guinness and you get a half moon, okay? But the bottom line is that, okay, because that would be a continuous mixture, right? But the point is this, without the U, you'll just keep bouncing back and forth. No, I want to do this. No, I want to do that. No, I want to do this. No, I want to do that, right? But with the U is sort of a negotiator that forces the two things to agree in some sense. So what happens is that in the limit, so we'll have x star, and we'll have, oh, this is, did I get that right? Is that right? X?
Yeah.
Oh, right. Oh, no, I was looking at the wrong thing. Okay, that's why I was freaking out, because, yeah, okay. This is v minus u, and that's x plus u. But, okay, that's good. So you'll have x star, okay, and you'll have v star, and you'll have u star. So those are the limiting cases. Let's assume this converges. In the limit, if this thing's not changing, then u has to be the same with each iteration, right? So in the limit, if the thing's not changing, then in fact, X star and U star have to be equal. Because that would be the steady state solution, right? So this is steady state. Okay? So what ends up happening is that the interpretation of this is this. We're out of time, so I'll let it go at this point. But what ends up happening is you have X plus X star plus U, and you have X star minus U, right? And X star plus U, if I apply this function h to X star plus U, I get this point, right, which is the output, X star. Because that's what the equation says. If I put X star plus U into H, I get, well, V is going to be equal to X star, okay? And if I have this guy, is going to go like this is going to be F. So you reach a balance where the H proximal map and the F proximal map go in opposite directions, but they result in the same output in convergence. Now, we're going to show, the augmented Lagrangian algorithm converges. We'll actually provide a proof of that. The proof for the convergence of the ADMM algorithm turns out to be qualitatively different. And we'll sort of not really do it at all. But I could actually give you a quick proof in class. But it's based actually on a different proof methodology, okay? But what are the takeaways? Okay, the takeaways are this. When you're solving these kinds of problems, often you have two very different functions to minimize, so you have to use very different methods. So the way you do that is by using these proximal maps, okay, which operate on just one function at a time in an iterative loop called ADMM. And for convex functions, this globally can be proved to globally converge to the global minimum. Read the notes. Next time what I'll do is I'll do some examples of how you use this for a particular problem, like enforcing positivity in a reconstruction problem, or doing total variation regularization. Okay?